Hello, this is a talk that I gave at the Electronics Packaging Symposium in 2015 that was co-hosted by the University of Binghamton and General Electric and was held at General Electric headquarters, global research headquarters. In this talk, I give an overview about how we achieve convergence when we use paper as an engineering material. And I do that by digging into an example of how we can make magneto-electronics on paper happen. In the talk, first I give an overview about the motivation. Basically, I give the definition or I tell my audience what I do really mean with convergence in science. Then I demonstrate how we can achieve convergence when using paper as an engineering material. And then with the specific example of magneto-electronics on paper, and specifically anisotropic magneto-resistance, I do catch up my audience first on the phenomenon of anisotropic magneto-resistance. Then I demonstrate the experimental work we have done in fabricating these anisotropic magneto-resistors on paper. Then I do talk about the numerical model that we use to back up the experimental results, and then the efforts we have put into optimizing these magneto-electronics on paper. Then I conclude with a brief summary and some acknowledgements. Now, to convergence in science, I like to cite Paul Alevisatos, who was a scientist at Lawrence Berkeley National Lab. That he was among several scientists that were interviewed about convergence in science, and I feel that, and I identify most with his definition to convergence. Paul says, I think all scientists are experiencing this phenomenon of convergence, and I hope if you are a scientist, you are also doing so. In the early days of science, there was only one science, so it's interesting to think about what made people think about divergence in the first place, and he's right about that. And he says that was simply to make progress, because the problems were hard, and breaking them down into disciplines, one could achieve a certain level of progress. Today, it's the case that we have convergence simply because the tools we get from each discipline are so sophisticated and the problems we tackle are complex. It's a fascinating period. Indeed, it's fascinating, and I do believe that when employing paper, we are able to achieve convergence that the world is in need of. I do believe that when using paper, we can achieve different aspects of convergence. And using this example depicted in this slide of this Chinese restaurants that opened up lately, I mean, there are many examples, fascinating examples about paper-based applications or applications and solutions and engineering devices that are based on paper that have basically achieved goals that were not able to be achieved with different materials. But I chose this very recent example of the Chinese restaurants because I will be able to draw the basically similarities between these convergence aspects and this Chinese restaurant. This restaurant is made almost completely out of paper. The chairs, the tables, the cooking pots, even the walls, some of the walls are made out of paper. And I do believe, talking about the convergence aspects, I do believe that when using paper, we achieve a convergence between the past and the future. Instead of looking at the future being paperless, because paper is not modern and is not contemporary, I do believe that the past should be part of the future. And we really think about the first papers that were made in China, which is basically the similarity that I draw from this example, and that the future of education can be still based on paper, that not using paper in education and not teaching handwriting is not what I do believe is going to be the right thing to do. When looking at these chairs in these restaurants, we see the shape of the chairs that's kind of artistic, but also you see that there's the mechanical stability that needs to be achieved, that could be basically derived or calculated by engineers and scientists. And so I see in this chair a convergence between arts and science, artists and scientists, two communities that may be detached when using different materials, but with paper we can achieve a convergence between both. I do believe that with the low cost of paper, I mean, this Chinese restaurant here, I heard it's pricey, but if we take paper and we think of the low cost of this material and how many solutions that are based on paper that were delivered to the poor, that the poor and the rich have access to the similar technology, basically similar functioning of the technology, maybe based on different materials, but to reach some kind of convergence between the rich and the poor, that they would access the same solutions, the same devices, the same standard of life. I do believe that when looking at this cooking pot that's on fire, that paper is more than what we think it is, that paper might withstand temperature, in this case heat, that may not be the most intuitive solution for someone who believes in more rigid materials like steel and ceramics, but with this example here, we see that when using paper, we would be able to make the impossible happen. And the most fascinating part for me is that usually many great ideas are born on paper. But once they're implemented, they basically leave the paper to become something different, to become a different material. But for me, right now, I do basically draft my idea on paper, and the implementation of the same idea is able to stay on paper, and basically the convergence between these two aspects is really fascinating to me. And the efforts we put into conversions between magneto-electronics and on the roadmap, basically to making also spin electronics happen on paper. I do look at the properties of paper being advantages, and some of them not being an obstacle towards this convergence, but rather a challenge, a drive to think out of the box, a drive to push this technology forward. I do think that the flexibility of the material paper, the foldability of the paper, allows a really easy way of making three-dimensional magneto-electronics. I think lightweight and low cost are beneficial. I do think that even though for most engineers that are basically used to the highly smooth surface quality of semiconductors, that the surface texture of paper shouldn't be an obstacle towards making this happen, that the moisture intake, the thermomechanical properties of paper, or the soil thermal properties or soil mechanical properties of paper, that can be overcome by rethinking paper. And so the example of anisotropic magneto-resistance that I will take today to basically show how we can make this phenomenon happen on paper. But before I do so, I would like to catch you up on what anisotropic magneto-resistance is. Anisotropic magneto-resistance was discovered by William Thomson in 1856. What William Thomson did, he took an iron bar and he applied electric current on that iron bar, and then he measured the electrical resistance. So he got a number, he wrote it down on a piece of paper, and then he applied the magnetic field on the iron bar and applied also an electric current. When the electric current was directed in the same direction as the magnetic force, he measured an increase in the electrical resistance. So that was a discovery. And then he applied the magnetic field perpendicular to the electric current on the iron bar, and he measured a decrease in electric electrical resistance. So basically that was his discovery, and he found out the same phenomenon happening in nickel. So iron and nickel happen to be ferromagnetic materials where the interplay of magnetization and spin-orbit interaction make this change in electrical resistance depending on the angle between electric current and magnetic force happen. And for your convenience, I do have here some transfer characteristics for different angles between electric current and magnetic field, where this transfer characteristic is basically a change in electrical resistance. And you see for the 90-degree characteristic from the zero magnetic field, with increasing magnetic field, the electrical resistance decreases. The opposite happens for the 0-degree angle, and this is what you see there on the bottom of the slide. What happens if you have a 45-degree or a minus 45-degree angle? And these characteristics basically are specified for different angles, and so this phenomenon is really used everywhere where you can think of, where linear position sensing, angular position sensing of any machine that might be in motion, that phenomenon is being used there. Or if you might think of the lid switch of your laptop when you close the lid, that's based on the anisotropic magneto-resistance phenomenon. The roof position detection of the convertible roof is based on anisotropic magneto-resistance, and the examples are countless. So in terms of making magneto-electronics and specifically anisotropic magneto-resistance happen, we've basically first took a piece of paper and deposited an alloy, which is called permalloy, which is an alloy of nickel and iron, basically two materials where William Thomson discovered the anisotropic magneto-resistance phenomenon. And stepping into his footsteps, we wanted to see what happens on paper when we deposit this soft magnetic material and measure basically the electrical resistance based on the angle between electric current and magnetic force. So as a reference, we took a smooth, rigid material, which is fused silica as a substrate, which we coated with the permalloy coating. As a second material, we took paper. Well, we are curious to know what happens on paper, and in order to separate the mechanical properties from the surface texture, we basically replicated the surface of paper onto an epoxy resin, and we coated that epoxy resin mold with the permalloy coating. And then we looked at the change in electrical resistance. Well, basically, for the reference sample, which is the fused silica substrate sample, we measured what we are supposed to measure, basically an increase in electrical resistance, and comparing that with the characteristics I showed you in the previous slide. On the paper and the epoxy samples, we see something similar to the plus minus 45-degree response that we found there. Well, the method we use to obtain these characteristics is the 4-point contact resistance measurement, which is usually not meant for soft materials. This is something that you push on a substrate. Basically, you indent into the coating, and if the bottom substrate is soft, that will not withstand that spring pressure that's being applied by the probe needles, you might get some side effects. So after doing some processing, we obtained these characteristics. Now, for the second configuration, where the electric current is perpendicular to the magnetic force, we have measured on the reference sample the decrease in electrical resistance. On the paper sample and the epoxy-based sample, which is the replication of the surface of the paper, we obtained a plus minus 45-degree angle response. Well, then, basically, we asked ourselves, why is this happening? I mean, this is happening on the epoxy and on the paper, which the only thing they have in common is the surface texture. So The hypothesis we put is that the fiber network is the responsible for that 45-degree shift. Basically, we have a shift between the two configurations we measured by 45 degrees, plus minus 45 degrees. So the fiber network, well, in this at this point of time in the presentation, I would like to look at the paper surface and then basically talk to my audience about what the paper surface looks like. And I would like to define the paper surface characteristics into four categories. Interroughness, which is the network topology, the interporosity, which is given by the microscale porosity, basically the empty spaces between the fibers. And if you look at each fiber, it has its own roughness, that's the nano roughness, and it has also its own pores, so that's the intraporosity. I also like to look at each fiber once coated as a distinct electrical conductor and a magnetoresistor. Now, in terms of magnetics, if you think about the magnetization, where you have the formation of domains and the domain walls, basically the boundary of each domain, and once the magnetization happens, you have a motion of those domains walls, enlarging of those domains, magnetic domains. And for coming from literature that's basically not paper-based magnetic literature, but any type of literature that uses a network topology to making magnetic coatings or magnetic systems, usually the network topology facilitates the motion of those domain walls, which is something very beneficial. However, the roughness you see at the fiber level usually induces a pinning of those domain walls. So you have here basically a trade-off between an advantages and basically a blocking characteristic, basically a surface property of the paper. So it's very interesting to see which one will basically win and which characteristic is more important and more decisive on the other when it comes to making anisotropic magnetoresistance on paper. And last, I would like to show that when zooming in, this is an AFM basically measurement of the fiber, you see a porosity and you see the nanopores. And once that surface is coated by a magnetic material, like for example permalloy, you have maybe, if all conditions are set, you may have a tunneling of electrons through those through that intraporosity, basically the nanoscale or the fiber level pores. As I said, we did the first experimental the first experiments using 4-point contact resistance measurements. And so basically to validate those results, we used a different method for measuring electrical resistance. And the first method, we are able to basically avoid any resistances occurring through the contacts, soldering the wires, and so on. But in this method, we will be including those resistances, but measure the resistance not through touching the paper surface, so not applying a pressure on the paper, but through measuring through contacted wires. And we do fabricate those samples in a shape of a magnetic stripe, because the magnetic stripe gives the direction of the electronic current once applied on it, and therefore I would know how the electrons are flowing or in which direction they are flowing. And we fabricate these stripes by means of shadow mask patterning, because it's the easiest thing. However, we are working on photolithography on paper, and we use a magnetic clamping to have a highly defined shadow mask contact to the paper and a highly defined pattern transfer or pattern formation of the coating. We use that with a combination of magnetron sputtering. And I forgot to mention that in the first set of experiments, we used also the same technique to coat those papers. So, when combining magnetron sputtering and a magnetic clamping, one might think, well, this might not work. But what we found out is basically in our setting, in our machine, the magnetic clamping was advantageous because we obtained a good pattern definition, we obtained a higher sputtering yield, and the magnetic properties of the coating as sputters were much better than when sputtered on a non-magnetic pellet. The magnetic stripes, we manufacture those also on a smooth surface, which we use as a reference, and the smooth substrate is the fused silica material we used in the first experiment. And then once we made these samples and contacted them, we measured the magneto-resistance. And what we found out is the following. Looking at the reference sample with the electric current parallel to the magnetic field, we have obtained the following characteristic. The blue curve is the change in voltage, and so it's change in resistance. And the orange curve is the change in magnetic field. And they both are shifted by pi4 phase. So basically you can move that peak of the blue curve to the middle, to the center of the chart. And so what we see here, basically what I have showed you in the first experiment, that you have an increase in electrical resistance once you have that configuration on a smooth surface. What happens on paper? On paper, we obtain a response that's here overlapped on the blue curve with a sign that's coming from the induced voltage of the contacts and so on. But this is the response you would get when having a 45-degree angle between electric current and magnetic force on a smooth surface. So here again, we have obtained that shift in electrical resistance. On the reference substrate, when we have a minus 45-degree angle between the electric current and the magnetic force, we measure the following response that's overlapped with the sine curve that's induced voltage from the contacts and the wiring. But this is something that we know. Now, looking at basically the response of the paper-based system at the same angle, basically the same angle between electric current and magnetic force, which is minus 45 degree, well, the electric current that we would think it might happen along the magnetic stripe, but we obtain a response where the electrical resistance, so the blue curve, and you see the second tip, that's very clear there, that the electrical resistance is increasing. So that's the 0-degree response you might basically obtain. So basically with the second experiment, we confirmed that the 45-degree shift is happening. And this is not dependent on the basically on the material. It seems like it's depending on the surface texture, and the same experimental result has been obtained whether using a 4-point contact measurement or a 2-point electrical resistance measurement. So in order to back up that result, we implemented a numerical model. In this model, we generate a statistic distribution of fiber paths between 2 points where we vary the fiber length and the fiber orientations in a square surface, an A by A surface. The width is A, and we basically measure the resistance along that path, assuming that the magnetic field is in the horizontal direction, and we basically look at the magneto-resistance of that entire path as the sum of the magneto-resistance of each of those segments that you see, each of those 2-point segments that are connected with each other. That's what I call a segment, and that magneto-resistance adds up to the overall magneto-resistance. And similar to how wireless networks are models, we found out that a uniform distribution of the fiber angles and normal distribution of the fiber length gives you basically the most realistic representation of the paper surface from what I've seen in SEM graphs or micrographs or the like. So we studied basically the magneto-resistance as a function of the fiber length and the coating pattern. So what basically we have obtained with the simulations is this graph here on the right side, on the top right side. The blue curve is the magneto-resistance of the permalloy coating on a smooth surface. The red curve is the magneto-resistance of the coating on a paper surface. And if you look at the shift between peak to peak of the blue curve to the red curve, it is a 45-degree angle. So this is again happening in the simulations where mechanical properties are not being modeled, local magnetic fields are not being modeled, basically just a homogeneous magnetic field and electrical resistance as a function of the network topology of paper, even a really smooth paper. So here also the roughness of the fibers is not being modeled, so the only parameter that's present in the simulation is the fiber network topology. And here again we confirm that 45-degree angle shift. And what we found out that this shift is independent of the fiber length. Whether you have small fibers or long fibers, you still have that 45-degree angle shift. If the coating pattern changes from a square, fully coated sample to a stripe to a meander with different dimensions, that pi/4 or the 45-degree angle shift is there. So there is no other explanation that the shift should be due to the statistic distribution of the fibers on the surface. And what we know from classical sensing or resistance measurements on smooth surfaces that the stripe geometry gives you a better response, magneto-resistance response, that meanders and narrower meanders and meanders with more windings give you a better magneto-resistance response. But also what we found out that configurations with smallest fibers and largest fibers give you the best magneto-resistance response. However, that 45-degree angle shift is there. No matter how the fibers are basically modeled or manufactured, whether small or long, and no matter how the pattern is of the paper, you still have fibers within that coating, and those fibers and those angles of the fibers, no matter how large or small they are, those angles make that 45-degree angle shift. So I came to the second part of the presentation where I talk about the efforts we put into basically finding which paper is made for this application, basically the anisotropic magneto-resistance on paper or soft magnetic coatings on paper. And so basically the goal that we set up is we want a coating that has lowest coercivity, basically lowest magnetic force you need to magnetize and demagnetize. Basically this is an indication for how sensitive your material is, but also how well this magnetic coating on paper can retain the magnetization within itself, that's the remnants, and for sure large permeability. So basically what we have seen, increasing the coating from 100 nanometers to almost 1 micron, we have seen that there is really no substantial change in roughness of the surface when increasing the coating. We are talking here of average roughnesses of up to 3 microns, whereas 1 micron of coating wouldn't change, basically wouldn't level up that roughness. Well, but still, with increasing coating, we have obtained a decrease in coercivity, and that's those red bars here in this graph. This is actually given by theory on smooth surfaces, which is happening on the paper substrates, where the yellow dots you see there is the theoretical model of how the coercivity of the coating on smooth surface should decrease with increasing thickness or coating thickness, and this is what we almost obtain or similarly obtain with the coatings on paper. What we also found out that actually the roughness of the paper is not a decisive factor for a better magnetic response. What we see here basically from a regression analysis that the R square, basically the Pearson coefficient, the square of the Pearson coefficient is largest for the surface roughness and is largest for hardness and Young's modulus, which are the mechanical properties, on basically impacting the relative permittivity, saturation remnants, and coercivity. Relative permeability, saturation remnants, and coercivity. And the factors of surface properties, geometrical properties, are less decisive on these magnetic properties. So basically what one might fear that the surface properties are really challenging for making magnetic coatings work on paper, it's basically the other way, that we have to think of the mechanical properties of each of the fiber, that these fibers, once coated, they won't warp and induce stresses in the magnetic coating, which basically worsens the magnetic response of those coatings on paper. What we also found out that surfaces or paper surfaces that are fibrous, that where you see really visibly the fiber, that's really fibrous paper, compared to a paper that's being smoothened, calendared, or compacted, those papers actually perform as good as they perform as good as each other, and that's an indication that, from what I said earlier, what we found in literature, that really the fibrous network is helpful for the magnetization process, for the motion of domain walls, basically lowering the coercivity. And last, what we found from electron dispersive X-ray analysis, that good news is that most of the papers that are commercially available are not made on an acid base because of the standards that were established in the last years, because a paper should last couple of 100 years, even 1,000 years, if you buy a really good book. And comparing this with the electronics that are on a 2-year cycle, buy and throw within 2 years, you see that once making something on paper, it might last forever. But also thinking about the fear that the acids and papers might attack your metallic coating or magnetic coating, that fear is not there, because most of the papers nowadays are made on a neutral or alkaline based solution. But what we also found out, that some of the papers are filled to make them stronger with molybdenum particles, which is a paramagnetic material. And once these molybdenum-filled papers are used, and once they are coated with a magnetic or soft magnetic material, you have basically superposition of these two differently magnetic materials, which might affect your final electromagnetic or magnetic response of the paper-based magnetic coating. In summary, what I showed you today, basically the efforts we have made towards convergence between paper and anisotropic magneto-resistance. What we have obtained experimentally is a shift of 45 degrees between the theoretical, the well-known transfer characteristic on smooth surface to the paper surface. And the hypothesis we have put is that the fiber network is the one that induces the 45-degree angle shift, because we were able to obtain the shift with two different measurements techniques. We have obtained the shift also on two different materials having the same surface properties. We were able to back up this hypothesis with a numerical model, and we showed you some efforts into optimizing these systems, and that the main conclusion we have drawn from these optimization efforts is that the mechanical hardness of the fibers is more decisive or most decisive on the magnetic properties of the coating. I think, or what we are trying currently to do, is basically also looking at that 45-degree shift in terms of how those domain walls form, and we want to do that with Moog microscopy, which is actually also made for highly smooth, polished surfaces. But we were already successful to see actually some information about the magnetization of the coatings on paper. We're also going to use atomic force microscopy to analyze the deposition, crystallization of those coatings, and we will assess the sensitivity, reproducibility, long-term reliability, and the functionality of these systems under environmental conditions like heat and humidity. And so, last but not least, where I come from, we do say that one hand by itself cannot applaud. So I would like to acknowledge some people. First, Professor Lutz Rissing from the Institute of Microproduction Technology, and from Purdue University, I would like to thank my student Matthew Stegeman, who helped doing some of the experiments. Meriem Akin from the Institute of Communications Technology for basically discussing and helpful conversations on the numerical model, and for collaborators from Purdue University, Northeastern University, Beloit College that we are going to be starting to work with, and for IP at Leibniz for funding this trip. And I would like to thank you for your attention, and I will take any questions you might have. Please, if you have any questions, you can also leave them below under this video. Thank you.